Hello guys, my name is Engineer Holiday. We want to discuss about transformer and we'll be looking at a lot about this topic. First of all, what the question we're going to ask ourselves is what is transformer? Now, a transformer is what is, let me draw a diagram first so that if I'm explaining, you will be able to understand what we are doing. Is a rough sketch. So everything I'm going to be explaining about the definition is in the diagram. Majority of things I'll be explaining. Now this is a rough sketch of what? Of a transformer. A rough sketch. Now, a transformer operates on mutual induction. And how? You operate on mutual induction to step up the voltage or step down the voltage produced by the alternating current. Is either you operate on mutual inductance to either step up the voltage or what? Step down the voltage produced from the transformer. So when we are talking about mutual induction, it operates on what? Mutual inductance, mutual inductor or inductance to what? To either step up or step down the voltage produced from the alternating circuit source. So alternating circuit source. Circuit what? Source. So in this case now, that means that number one thing you must know about this is that it operates on mutual inductance. It operates on mutual inductance to change what? The voltage produced from an alternating source. That's what we call a transformer. Don't also forget that there are, in this circuit, there are some things I want to show you that you need to understand. Number one is that there is a load here. Load. There's a load in this part that is connected to the secondary coil. This is what we call the secondary what? Coil. Then we have another what? Coil here, which we call the primary what? Coil. This is what? The primary what? Coil. So we have two coil here, the primary and the secondary coil. Now this primary coil is connected to the AC main supply. So it is the source, the AC source that supply what? Voltage to the primary. So the primary now takes its voltage from the source. Now while the load is connected directly to the secondary, so the consumer always what? That consume the supply from the AC is at the secondary. Now what are the things I said concerning this now? Don't forget that I say step up, step down. That means that there are two types of, majorly at this level, there are two types of transformer. We have the step up transformer, and we have what they call the step down transformer. The step what? Down transformer. Step downward transformer. So we have two types of transformer, the step up transformer and the step down transformer. I'm coming down to that place, to this particular type of transformer. Now, number two point I want you to understand concerning a transformer is that it operates on the principles of electromagnetic induction. It operates using what? The principle of what? Electromagnetic induction. Electromagnetic what? Induction. So if it operates using the principle of electromagnetic induction that was described by Faraday, it was Faraday that explained the principle of what? Electromagnetic induction. Now the next thing we should look at again here is that when will a particular consumer require is to step up a voltage transformer? When will it require a step up voltage transformer or step down? We use step down transformer for in home where TV is required, television and all that. To operate such home, we use step down. Then to supply to power stations, we use step up where high voltage is required. That means it required what? If you need high voltage, you need what? It depends on what they need at this end. If there is a need for high voltage. Now let me explain something. Don't forget that whenever the number of primary coils, these are called the coils. This is the laminating what? This is the laminating core. I will explain that later. Why we call it laminating core. Now, whenever the number of turns on the primary, that means number of coils in the primary, is higher than number of coils in the secondary, we call this one a step down transformer. Whenever the number of turns in the primary is higher than the number of turns in the secondary, we say it is step down transformer. But whenever the number of turns in the secondary is higher than number of turns in the primary, we call it a step up transformer. That means note that. Similarly, that means that what? When the number of voltage in the primary, what? The magnitude of voltage in primary is greater than voltage secondary, is still what? Step up. Step down. But when the what? VP is less than what? VS, we call it what? A step up. Step up. So this is a step up transformer and a step down transformer. Now, don't forget that for a transformer, there are things we should know about what I've just labeled now. Don't forget, I told you we have the primary turns and we have the secondary turns. Now, let us assume that in this transformer, we want to what? Assume an ideal transformer. An ideal transformer. When I say an ideal transformer, we say a transformer that what? The losses is minimal, or where the efficiency is equal to what? 100%. Where losses is what? 100% efficient. Now, if the efficiency is 100%, it means that what? The transformer is an ideal transformer, meaning that energy loss is zero. Now, the power output is equal to what? Power input equal to power output. And therefore, we say that what? That ISVS equal to what? IPVP. Now, in this case, no losses is experienced. Energy loss is zero. No loss in the transformer. And this kind of transformer is not visible. So we say it's an ideal transformer. So such a transformer, we say output is equal to power input. So in this case now, what we expect from here. Now, don't forget that E is proportional to N. V is proportional to N. That means that the EMF that will be induced, or the EMF that will be induced here, will be linking the secondary. That means there is a changes that will occur from primary to secondary. That means when there is a setup voltage at the primary, it links the secondary vote to create a voltage at the secondary. That's why we call it a mutual inductance. Mutual inductance is that word. As the word, the primary is like is on top of the secondary. Near the primary, we would set a flux that will link the secondary. Now, first, let me show you something. Remember that from this formula, we can say Vp over Ip equal to what? Okay, let me say you divide both sides by Vx and Ip. If we divide both sides by Vs and Ip, what do we have? Now look at what we are going to have here. Let us see what we are going to have here. Now, if you have what? Ivs divided by what? Ip and Vs equal to what? IPVP divided by what? IPVs. What do we have? This one will cancel this one. We have Is over Ip equal to what? Vp over what? Vs. Take note of this. Now, recall that I said what? That V is proportional. That means the voltage at this primary coil is determined by what? Is depending on the number of turns that will be formed, that the number of windings on the primary. Then the number of windings on the secondary is depending on the number of coils in the primary, in the secondary. So if you check this one very quickly, you have 1, 2, 3, 4, 5, 6, 7, 8. Yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this transformer I just draw now, more or less like a step up transformer, because the number of turns in the primary or coils in the primary is higher than the number of turns in the secondary. So basically, since V is proportional to what? To N, we can say Vp is equal to what? Np over Vs equal to what? Ns. So if you combine the three of them together, what we are going to do now, combine this and this, we want to have it as what? Is over what? Ip equal to what? Np over Ns equal to Vp over Vs. So that's what we are going to have there. Now, having gotten that, now we understand basically that the Vp that we have gotten is the voltage across the primary. Don't forget, the Vp is voltage across the primary and the Vs is voltage across the secondary. So when we are dealing with what? Vs is voltage, potential difference across the what? The secondary. While what? The Vp is what? Voltage or potential difference across the what? The secondary, across the primary. So in this case, you must understand that the voltage across the primary and the voltage across the secondary is depending on the kind of transformer you are working with. Because now we can now conclude that what? This formula for transformer is visible when you are dealing with an ideal transformer where no losses, where the power output is equal to power input, where the transformer is operating at 100% efficiency, 100% efficiency, 100% efficiency. So now another thing again you must note here is that the current is inversely proportional to what? To the voltage, and inversely proportional to what? To all. Let's say V is directly proportional to N and inversely proportional to what? Current. So that means the side with the higher number of turns will have a what? Lesser current induced here. Now don't forget that why we use a laminating core, this is a core, is because to what? Eddy current losses to be minimized. Eddy current is that current that is induced as a result of what? Magnetic flux created in the what? In the core. Now, don't forget that the eddy current is what? Is that loss that is created or that is formed in the transformer as a result of energy due to it that is created or produced as a result of a circulating current. A circulating current produced as a result of what? Induced what? Magnetic flux in the transformer, in the transformer. And this one is what? That's why we laminate. So when we laminate the core or we insulate the metals, the iron core, when we insulate it, it tends to reduce the what? The heat, because the energy loss now is due to heat, and that heat now is as a result of the circulating current. That circulating current can also be called eddy current. Don't forget, as a result of magnetic flux created due to this particular current in that AC circuit, or as a result of this AC source. So in that case, how do you minimize it? Just use a what? A laminating core as what? As your core here to minimize eddy current losses. That's why I told you, I will explain why we always use laminating. This LAM, laminating core. Another thing again is that, let me give us a real cases, a practical word transformer. Now, a practical transformer experiences the following losses, and these losses can be reduced as a result of what? These following what characteristics. Number one is what? Copper losses. Copper losses. Copper loss is what sometimes we call it what? Heat losses. And this is as a result of heat that is eating the coil. It's a result of eating the coil itself, the coil. So when you eat the coil, there will be what? A lot of heat that will be lost through that coil. And that's why we advise you to use a low resistant what? Coil. A low resistant coil. So that when you use a low resistant coil, it will minimize the heat, because heat is generated as a result of the resistance. Don't forget, resistor helps to dissipate heat in a circuit. Now, if the resistance is now lowered, it will help also to lower the heat that will be lost in that coil. So to reduce it, you use what? Low resistance what? Coil. So we say this is a coil loss. So we have coil loss and coil loss. Coil loss. Coil loss and coil loss. Coil losses and coil losses. Now, this is one of the example of what coil losses. Now, don't forget that the heat that will be generated from this wire is I square RT. Each energy is I square RT. So when you reduce the level of resistance or you lower the resistance in the coil, it will minimize the heat. The next one is what we call the eddy current losses. Eddy current losses. These are losses that are what? Created as a result of energy loss due to heat. And this what? Energy loss due to heat is what? Is created as a result of circulating what? Current in the core. Hello, circulating current in the core. So that means it's a core loss. Circulating current in the core due to what? The induced what? Magnetic flux that is produced by the AC. So note that now. Note the point I just mentioned now. Number one, eddy current losses is an energy loss due to heat. Number one, that means it's due to heat in the what? In the core. That is as a result of what? Circulating current. That current is what we call eddy current that is induced in the core as a result of magnetic flux. What is magnetic flux? That is created by the what? By the AC. Because this magnetic flux created in the primary, we are supposed to link the secondary without any linkage. But if there is a linkage, then there will be flux linkage loss. And that brings about what? This one, laminating the core. Laminating the core. So this is a core loss. Or if you now see this one in the exam, insulating the what? The metal. Better. Now, the next thing is what? Is the kind of losses that occur in practical cases is what we call hysteresis losses. Hysteresis. Hysteresis. This loss that I'm talking about now is loss that occurs in the what? Hysteresis. They are losses that occur due to magnetization and demagnetization of what? Of the AC. Don't forget that this is an AC source. Now, let me show you something. We understand from O level that in AC circuit, this is a flow that occurs. Now, during this process, there is a magnetization. During this process, there is a demagnetization. Then here is what? Magnetization. This process is what? Demagnetization. Magnetization, demagnetization. So during the demagnetization process, there are losses that is occurring in helping the what? Because when you are during magnetization, the magnetic domain align themselves in a way that they become magnetized. The magnetic domain align themselves in a way that they will become magnetized. The magnetic domain is what? The magnetic molecules in the domain, because the domain of a magnet is where the magnet resides, magnetic molecule. The smallest magnet is what we call magnetic molecule. And don't forget, even as small as a magnet, they will have the north and south pole. We are told that when you keep pulsing a magnet, it continue to retain its dipole properties. Therefore, when they become magnetized, they align, they move in one direction. Don't forget, one way to magnetize a particular magnet is what? Connecting them to a DC. But one way to demagnetize a magnet is connecting them to AC source. So when you connect them to AC source, the magnetic molecule inside the magnetic domain will magnetize. At the point we demagnetize, during the demagnetization, they realign themselves again. Then when they magnetize again, they realign again. This realignment of this magnetic molecule in a magnetic domain that is occurring as a result of magnetization and demagnetization in an AC source of this kind in a transformer is what leads to what? Hysteresis losses. So those magnetization and demagnetization that occur, that now brought about friction, because friction will now come set into place into the core. Now because this one is a core loss. Please take note, core loss. That means I've mentioned two core losses now. I've mentioned what? Eddy current losses and hysteresis losses. These are core losses. Then this one is what? A coil loss. So now the friction that sets into place that causes energy losses as a result of magnetization and demagnetization of the what? Of the core used in the transformer is what brought about what? Energy losses. And brought about what? Hysteresis loss. And the best way to reduce it is using what? Soft iron core. When you use a soft iron core, then it helps. Don't forget, iron naturally they are easily magnetized and easily magnetized. So when you use a soft iron, it helps for easy magnetization and demagnetization of the wall of the core. Now, the last one is what we call the flux linkage loss. Now, in this flux linkage loss, we notice that the primary, when you create a magnetic flux at the primary, it is not all the link, it does not link all to the secondary. Some are lost as a result of linkage in the flux, in the magnetic flux, as a result of what? Improper design of this core. So in this case now, what we are going to do now is that when you are what? The coil, this one is what we call the coil itself. Because if the coil is properly designed in a way that when the primary is created, magnetic flux is created in the primary, it's supposed to link the secondary coil without any losses. But we notice that there are losses during the linkage from primary to secondary, which as a result of mutual inductance that is set up in this transformer. So how do we now reduce these losses? Is to use a very effective design. Effective design will help us to design of the core. So if you use effective design of the core, it will help us to maximize the linkage from primary to secondary. Or sometimes you say using soft iron core. So now in this case now we have talked about the 4 things that we need. 1, 2, 3, 4, the losses that we need here. Soft, this is soft, sorry. So now let's talk about since losses are now involved, it means that primary the power input is greater than power output here. It means that there are losses in this transformer. It means efficiency is no longer is not 100% now again. Now since efficiency is not 100%, what is now the formula for efficiency of the transformer? Is power input or power output rather over power input times 100%. So this is the formula for the efficiency of the transformer. Most applied the power output is IXVS, set up at the end, at the secondary end. Power input is set up at the primary end, which is knowing fully well that power equal to IV. You know that now, or I square R or V square over R. So times 100%. Now if they did not give you the secondary voltage, we can get the secondary voltage by multiplying the current of the secondary times resistance of the load. This load has a resistance, so you can get resistance of the load multiplied by secondary current can give us the Vs. So in case you are not given Vs, so don't forget that. Then the power input can be the power of the AC, the supply. So most of the time the power of the AC is equivalent to power of the primary, so which is IPVP. The power of the secondary is ISVS. But sometimes most of the time this one is VRMS. The AC voltage is VRMS. It's giving us as in terms of VRMS. But what is now the maximum voltage that we set up here? The question is, we can get the maximum voltage that will be set up by using this relationship that said VRMS is equal to maximum voltage divided by root 2. So let's say this one is for the primary. We can also say VRMS of the secondary equal to what? Of the secondary is equal to what? V naught of the secondary divided by root 2. This is primary. Similarly, IRMS of the primary is equal to what? I naught over root 2. While VRMS or IRMS of the secondary and setup is equal to I naught over root 2. Since IRM, the voltage that is produced from the source or from the AC mains is voltage VRMS, root mean square voltage. That's what we call it, VRMS. Has a relationship with maximum voltage, similar to secondary. Then similar to current also, the IRMS of the primary also have the maximum current on the primary and also have the maximum current on the secondary. It depends on question. That is the interesting part where we are going to look at question. In our next class, we are going to see question on transformer, where we are going to properly analyze different kind of questions that could come your way in transformer. I believe you have enjoyed the class, and if you enjoy it, please click the like button and subscribe if you are just watching my video for the first time. And if you are a returning viewer, thank you for always standing by us. God bless you. I remain in generality. Thank you.